Now we're going to talk about the lift on airfoils experiment. It's going to utilize the same small subsonic wind tunnel that you used for the boundary layer flow experiment. We're also going to again be using the digital multimanometer, which you are all familiar with, and it's going to be read again by that averaging program on the computer. So the way the lab works, and you can pull out the model by simply just grabbing and pulling it. It fits in that bottom slot. If I take the top off, you can see that here's our airfoil section. All right, you can notice that this is an asymmetric airfoil. And what you are going to do is you are going to measure the static pressure going around the upper surface. And you can see all these small tiny holes here. Those are static taps, and they are sending the pressure through this tubing, which is eventually sent to the manometer. So we have some ports on the upper surface, and we also have some ports on the lower surface. And so the lift force, right, can be calculated if you know the pressure times the area on which they're acting. So we can do a discretization of the area on the top and the bottom, and the lab will talk you through how to do this numerical integration scheme to approximate the lift force. Now, the angle of attack is going to be changed by just loosening this knob right here, and then you can change the position relative to the piece of wood. And what I want you to do is notice that, let me see if I can, the easiest thing to do is to look at the trailing edge and point the trailing edge at the degree measure. But I want you to note that if you have, so you see here, I've put the trailing edge, and it's not at 0, it's below. It's about at 5 degrees. But if I hold this, you'll see that it does indeed look perfectly horizontal. And so this corresponds to 0 degree angle of attack, okay? So the easiest way to measure the angle of attack is, again, to point the trailing edge at some degree number, but recognize that it's about 5 degrees off. So if the trailing edge is pointing at 5 degrees, it's really at a 0 degree angle of attack. If I pointed it at 10 degrees, it would be at 5 degree angle of attack, and so on. And you're going to change the position of the airfoil between -5 degree angle of attack up to 20 degree angle of attack for a single free stream velocity. All right, I'm going to throw the model back in the tunnel. Now, the pressures, the way I have them set up, is the upper surface is, and you can kind of see that they're all labeled. Here you see 8U for 8 upper. But the stagnation point probe, the one right at the leading edge, is going to be on port 0. And then it's going to go along the upper surface, 1, and it's going to go from the front, or towards the leading edge, to the back. And so the upper surface, we go all the way up to number 9. And then I have the first port on the lower surface hooked up to number 11. So there's nothing on 10. So this is the 0 is the stagnation, and then it goes along the upper surface for the rest of the 9. 10 is blank, and then the ones on the lower surface go 11, 12, 13, 14, 15, and so on until the end. Okay, so what you do is you're going to set the tunnel to one particular velocity. You're going to acquire all of these pressures, and then you're going to change the angle of attack, do the same thing again, and do that for all the angles of attack that we mentioned. Okay, so a single velocity at the different angles, -5, 0, 5, 10, 15, and 20 degrees.